So we want to look at some examples and look at exactly what's happening in this example. The examples we'd like to look at are shown here in this actual assembly program. We've got a couple of things to note here. Count is a variable that we set to 0. Var is a variable we set to 0. And there are some various different kinds. Here's where the program starts here. There's some various different kinds of register access. We're going to look at those here. And we'll look at each of these examples here in detail and see what happens. So the first one here, this is the address where this program is stored, 8000 hex. The number that's actually you'll find in there is 540A, and that is actually the machine language representation of this assembly language instruction, add word R4 to R10 and store it in R10. Here's the comment, R10 equals R4 plus R10. And similarly for all the other lines here, this is a standard way of looking at assembly code. These red things are the machine code that was generated. And these are the line numbers in the file over here, and these are the addresses at which things are stored. So let's look at the different kinds of addressing we're going to look at closely. First one is register. The second one is used here as indexed register. The next one here is indirect register, and indirect's auto increment. And then we've got symbolic, which is really PC relative. Then we have absolute, and we have immediate, and we have when the constant, the immediate constant is one of those special ones, -1, 0, 1, 2, 4, or 8. You can use those registers 2 and 3. So this could make it go a little faster. Okay, so how does the instruction cycle work? In general, there are 6 phases for each instruction. Now, you can have one clock, but there can be different phases of that clock. In other words, like you can have a sine wave and a cosine wave both running at the same frequency, so that would be one clock, but those are 2 different phases. Sine and cosine are different by 90 degrees. So what happens when we're making a computer, we can use one clock, and then we delay it by a certain portion of a cycle, maybe 1/6 of a cycle, and we can make 6 different phases of that clock to execute different code. So if you notice, these 6 different things are all executed and could be executed in one instruction cycle. So here's how an instruction cycle normally works. First thing that happens is the instruction fetch. So you really need to obtain the machine code instruction from memory. That's what's happening on that phase. Then there's a phase where we have some logic which decodes whatever that machine code instruction was to determine how to execute it. Then you have some operands usually, and the first one you fetch is the source operand, and then you fetch the destination operand, and then usually you use the arithmetic logic unit or something like that to execute the result. And lastly, you store the result in the destination operand. So in some cases, not all 6 phases of the thing are required. Some like a jump instruction might not need all these phases. But in general, these are the phases that we go through for an instruction cycle. Let's look at that first instruction. Remember, it was an add word, whatever word is in R4 to whatever is in R10, and then store the result in R10. So how would that work? Notice over here we have memory, and this would be at address 8000 if we're getting this from that program we just looked at. And the number 540A is stored in there, and that was the machine level language instruction for this guy right here. And over here we have, this is the instruction register. That's where we're going to store what we get. Eventually this 540A will go in there. This is an adder, which is used to sometimes when we have an indexed kind of addressing. This is the arithmetic logic unit, which does things like adds numbers for us. That's what we're going to use for this plus operation up here, or the add. That's what's going to do it. And over here we have the registers. R0 is the program counter. R4 is called out right here. That's our source. And then there's R10 as our destination. So let's just kind of see how this all works here. So the first thing that happens is, if you notice this opcode, this machine code you got over there, it says the source address is 00. So that means this is a register mode. Register mode is 00. And so let's see, the first thing it does is it looks at the PC and goes out and grabs that machine level instruction. It puts it in the instruction register, and then the decoding logic tells it that this is a register mode address. So we're looking at the first kind of addressing here. So now the instruction register has the machine code in it. So now the program counter needs to be incremented by 2, so it's ready for the next instruction. And then the program counter actually moves down 2. And then we take, because it was a register thing and register mode, and the source register was R4, we connect that, put the contents of R4 into one of the ALU inputs, and then we put the contents of R10 into the other ALU input, and the logic, so we'll say this is an add register, so it will add the 2 and put the result back into R10. That's doing the thing, and then putting it back into the destination address. And basically then we've completed the instruction here. Whoops, went too fast there. So that was a one-cycle instruction. So now let's look at mode 01, which is the indexed mode, indexed addressing mode. We'll look at the next line down, the add word. It's going to take whatever's in memory 6 plus, it's going to take memory 6, and then it's going to read whatever number was in register 4, add that to 6, and then it's going to add that in to register 10 and keep the result in register 10. So the program, the way this is encoded in assembly language is you've got 0x541A, that's the add.w instruction, but then it also has this 6, the 6 in front of R4, and it has to store that data. So this is really a PC relative thing. In other words, it needs to know that it starts at address 6 and it adds whatever's in register 4 to get the address, the number that it needs to add into register 10. So let's just kind of watch and see how that all goes. So the first thing that happens is we got the instruction here, and notice you got on top is the machine instruction. That's the first word, and then the second word. Remember, it says some of those instructions took 2 words. This is one of them, and it has a 6 in the second one, and the first one has a 5, 4, and then 1A. That's the machine code. So as we execute the machine code, the first thing it does, the PC is read, and it goes out and it reads the machine code instruction there at where the program pointer is pointing, and it gets 541A, which it puts in the instruction register in the CPU. Then the PC is incremented by 2, and then the PC moves down 2, and then it goes out and reads again that 6, and that 6 is then added in the adder with the contents of register 4. So those two are added together, and the result is the source address. The source address, that adder, gets the result, and now it uses that result to go out to memory and get the number at that address, and that number is put into the arithmetic logic unit, and that in one input of the arithmetic logic unit, and then whatever's in R10 goes into the other logic unit. Okay, so what is happening here? There it is. Whatever's in R10 goes into the other logic unit, and the result goes back into R10. So that's basically what was going on there, and that's how the indexed addressing works. It took 3 instruction cycles, because first of all, the first instruction cycle had to read the machine code. The next instruction cycle had to read the 6, and the next instruction cycle had to finally get the data out of that that address, add the data to what was in R4 and get that out, the final thing that went into the ALU, and that's the the third cycle there. Okay, so now let's look at indirect registers. So this is, we're just going to look at whatever's in R4, and that's going to give us the address of one of the operands, and then we're going to add that in with R10. So we start out just like before. In this case, we only need the machine code or machine instruction there. This is going to be a faster instruction. So let's just look what happens. So there's the machine code, that's 542A in binary, and you can see the address mode is 10, the source address mode is 10. You can also see the 5 up in front, the 0101 is a 5, and the 4 is 0100, and then 2 is the 0010, and then the A is the 10, that's the destination register. So first thing, of course, we go out from the PC to the memory, grab that, put it in the instruction register. The PC is incremented. After the PC is incremented, then that machine code is, or machine language is decoded, and it tells us to go to register 4, and whatever's in register 4 tells us where to go in memory to get the thing we're going to add into the ALU, and that is added with register 10, and we finally get the result there. So this is a two-cycle instruction. It's a little bit faster than the last one, but not as fast as the all complete register one. Okay, so let's look at the auto increment mode. This is very similar to the indirect that we just looked at, except it adds the increment on the end. And this still takes 1 cycle. So let's look at what happens. So first of all, we go to the PC, and we get, the PC tells us to go out and get that 543A, and there it is, 543A. The 3 is the basically the source is 3 tells us it's an indirect auto increment mode. So That tells us then we need to put that into the instruction register. Once we got it, we decode it. It tells us to take, well, we got to add 2 to the PC. That's the first thing to do, and move the PC down. And then you have to take what's in that decodes and says get what's in register 4 and go out there and grab the memory at register 4. So there it goes and grabs that, and it adds that into connects that one input of the ALU, and then it connects R10 to the other input, or it actually, I'm sorry, has to add has to put 2 in the adder because we have to auto increment this register 4. So you add register 4 with the 2, and you get a new number to put in register 4, and then you have to take what's in register 10 and put it in the ALU, and the ALU will add them up and put the result back in register 10, and then you're done. But this was still only 2 cycles. So we want to look at addressing mode variations. Let's look at the symbolic, which was when you're using a symbol, and let's look at the absolute. That's when we tell it just go out to grab at this actual address. And also let's look at the constants. How does the constant generator work? So what we're going to do is we're going to look at the PC relative, a way of doing things. And so we've got M. What we're going to do is we're going to take count. Count was set in part of the program to be a certain number. And so basically whatever is stored in count, the number count was set to 0, so we're going to put that into, add that in with register 10. So let's see what happens. PC relative. So here we go. Here is the 2 memory locations there. And so we've got on top the machine language instruction, and on the bottom we have the C, which is 12. That's the last 4 numbers on the red on the right on the second one there. So let's see what happens in symbolic mode. This is using register R0, which is the PC, the program counter. So first of all, the program counter is used to go out to get the the next instruction, put it in the instruction register. Program counter is incremented, and the program counter is moved down, and then we go out and read the next one where the program counter is now. And that program counter, C, is added into the adder, or put into the adder. And then we take the program counter. This is similar to last time, only we used register 4. This time we take the register, the program counter instead of register 4, register 0 instead of register 4. And those are added together, so now it goes out to an address wherever count is. That's where it is. Count was like 12 addresses below where this is in the program. And so we go out to count, we grab the data there and run it into the ALU, and then we grab the data, or we let's see, what did we do? We need to move the program counter down again, and then we have to grab the data in register 10, move it into the ALU, and then the ALU result goes back into 10. And this is actually a 3 instruction cycle again, because you can notice it takes more instruction cycles when you have more memory accesses like we had to do here. So that's symbolic mode. That's what happens, when we put a variable like count down at the bottom of our program to call it that. So then we've got absolute mode here. Absolute mode basically says go out to the address of whatever's, in this case, whatever's in count, and that will be the, whatever's at that address that count is pointing to. That's what we want to add to register 10. So this works kind of like, first of all, we're going to get the, we're going to get the two words that we need. The top one is the machine code. The second one is the data, which in this case is C018. That's the actual address where count is. And then let's look at how this thing is executed. So the program counter goes out and grabs the data the program counter is pointing to, puts it in the instruction register. The program counter is incremented by 2. It's moved down. Then the program counter is used to go out and get the data, which is the C018. That's then put into the adder, and then we're not going to add anything really onto it. We're adding 0 onto it because that's where we want to get it. It's absolute mode. And the result of that goes out to where count really is. It's actually at address C018 in this example here. And then that number from where count was pointing. I mean, count had C0. Let's see. I guess what was in count here. Yeah, right. What was, so it went out, and I guess count was pointing to C018. And so then that number, whatever's in that address, he's at where count was pointing, goes into the ALU. Then we need to move the program counter down again, and then we need to grab the thing from register 10 and add it into the ALU, and then the result goes back into register 10. So that's a 3 instruction cycle thing right there. Then we have the immediate mode. That's when we're adding a special number like 100. By the way, 64 is the same thing as decimal 100. So let's see how this would work. So it's encoded by the, you got the 503A, and the 3 basically tells us they're in this immediate mode. And the next number in there is the 64, which is 100 in decimal. So let's look at how this is executed. So the PC goes out, gets the machine level instruction, put it in the instruction register, and then the PC is incremented, the PC is moved down, we read the 100 or 64 out of the next memory location, and then that data is actually added into the ALU. The next thing is we grab, let's see, we got to move the PC down again. Increment the PC, move it down, and then we got to take what's in register 10, put it in the ALU, and put the result back in register 10. And that's 2 instruction cycles to do that. And then the constant generator, number 1 was a special constant, one of those special constants, so this thing will be encoded in machine language with a more efficient, a faster instruction, and also probably won't be as many memory locations to encode this, so it will go faster and be less memory used. And this add instruction, if I change that 1 to a 100, then it's going to take more memory, and it's also going to take longer. So this is a special case. The machine level instruction, assembly instruction looks basically identical except the number we're using. But the machine code is actually quite efficient for this special, it's one of those special numbers. So let's see how this thing works. So we have the PC first. First of all, there's the opcode. It's only one machine level instruction. Go from the PC out and grab that, put it in the instruction register, and then this says its AS is 1, so we're going to increase the increment the PC by 2, and then move the PC down, and then we're going to grab that special constant 1 from one of those registers, and we put it in the ALU. And then we grab the contents of register 10 and put it in the ALU, and the result goes back into register 10, and that only took us one instruction cycle. So, because that was a special number 1, it only took one instruction, and it took one cycle. So, one word in one cycle. So that was very, very nice, really quick. Now, there's a 3-word instruction. This is like really complicated because both the source and the destination are symbols, and so let's look and see. Basically, it says variable gets whatever's in count plus whatever's in variable. So this is going to take quite a bit more because we've got to do both on the source and the destination, and we're going to need like 5 words to do this, and it's going to take a bunch more cycles too. So let's see what happens. So it takes 3 words to turn the assembly into machine code here. First thing is the PC goes out and grabs the machine code, and that's put in the instruction register. And that instruction tells us we're going to need 2 more words. So first of all, we increment the PC, move the PC down, go out and grab the next word, and we put that over into the adder, and then we increment the PC. I guess we add put the PC in there, and then we go out, and after the result of the adder goes out to count, and that gets the source all set up. Now we need to do the destination. So we go out with the PC and get the destination, put that in the adder, and put the PC in the adder, and then the result tells us to store the thing in var. So we get that, whatever's, in var, we're going to add that to itself, right? So then we increment the PC and move the PC down, and then the results of the ALU goes back into var. So that was 6 cycles, and it took 3 words, plus the memory location needed for count and the memory location for var. So really took 5 words to do that. So that's a good place to stop for this video, and you can think about those things. Go back and look over those slides.